Welcome. Chain rule and implicit differentiation is going to be the topic for this lesson, and this course has yet to discuss the most important, 100%, the most important differentiation rule, the chain rule, because ultimately we're not able to take the derivative of any function right now. That's true. Of course, we already learned a whole bunch of stuff. Yeah, we know how to find the derivative of, for example, this complex function where 2x multiplied by sine of x plus x cubed. So it kind of seems we learned a lot, but it's kind of true. However, if I replace now x, even now, yeah, I replace x by 3x, that will be the end. So it will stop us. We won't be able to finish and find the derivative of this function. So we need to develop a tool that will teach us to take the derivative of the composite functions, and that will be the chain rule. And surprisingly, it adds really versatility to the rules we discussed previously. So let's master the chain rule. And it's in fact, that's very simple. So the derivative of the composite function, right, f of g of x, is just gonna be the derivative of outside function, f of g of x, multiplied by the derivative of inside function. So it's very easy to remember the rule, the chain rule. The derivative of outside function, f prime of g of x, multiplied by the derivative of the inside function, g prime of x. That's it. Or of course, we can also now state kind of strict theorem here. So if you have the function y, so we have y is the differentiable function of u, and u is differentiable function of x. It's a different function, g. Yeah. Then the derivative of the composite function y, dy dx, with respect to x, right? That will be the derivative of outside function, dy du, multiplied by derivative of inside function, du dx. Or equivalently, this. So these are the same things. And that's also kind of easy to remember, because so we want to find the derivative of y in terms of with respect to x, right? So dy dx, and that will be the derivative of outside function multiplied by the derivative of inside function. And if you can, it's a kind of mind trick, right? If you look at that, and that's easy to remember, because if you think in terms of algebra, then we can kind of simplify dy, right? Cancel out dy, and yeah, that will be du, cancel out du, and that will get dy dx. Yeah, sure, it works. So the rule is not hard, genuinely not hard. So therefore, of course, we can derive the formulas, but I'm not going to waste time for that. You can check it out in the lessons notes. We are going to practice now. Practice and practice and practice in order to master the chain rule, and then you'll be able to take the derivative of any function. You'll be that good. So let's start that. All right, so the first example, 3x squared plus 5, and that all to the power of 5. Good, yeah. So we want to find the derivative of this function. And we see, what's the outside function? This is just some something to the power of 5, right? So what's the derivative? We need to take the derivative of outside function. So that's just the power rule. Yeah, you see something inside. So this is just some function, something inside. The outside function, that's just the power rule. That's just about the power rule. Now I want to take the derivative of the outside function. That will be the power rule. That will be just bring down the 5 and multiply by the, and then subtract 1, right? So this is it. This was the derivative of outside function. Wonderful. Now we look at the inside function. Inside function is 3x squared plus 5. Good. And we'll look at that. And so I want to obtain the derivative. So what's that? That will be 3, constant stays the same, right? And again, the power rule, bring down 2, and subtract 1, 2x. And what's the derivative of 5? That's 0, right? So this is it. the derivative of outside, so that's f prime of g of x, and this is inside g prime of x. Very simple. So this is the answer. Yeah, of course we can simplify that, but it's not super important here. Okay, it will be, I don't know, it will be 30 3x squared plus 5 to the power of 4 x. So this is it. All right, so what was the first function? Let's continue practicing. Next one will be sine of 5x. Yes, what's the outside function? That's sine, right? So what's the derivative of sine? That's cosine. So it's cosine of 5x. So this is the derivative of outside function. What's the inside? Inside function, that's 5x. Now we'll multiply by the inside function. The derivative of the inside function. The derivative of the inside function is going to be 5, right? Because constant stays the same. But x, the power rule, that's going to be 1. So that will be 5. So the answer is 5 cosine of 5x. This is it. Next one. Oh, interesting. E to the x squared. Now, what's the outside function? E, right? E to the power of e to some power. So this is our outside function. What's the derivative of e to some power, right? That's just e. It's so e to the x, as we remember, was the derivative of e to the x as just e to the x, right? So it's going to be e to the x squared. This is the derivative of outside function, and we multiply by the derivative of the inside function. Inside function here is x squared, so that will be 2x, right? We apply the power rule. So this is going to be the final answer. And I think that was good for the warm-up. Now let's try to solve some complex problems. All right, so next example. Let's take the derivative of this function. So I want to find the derivative of this thing. Or the same thing again, y prime. I want to find y prime. So that will be, again, we see that the outside function, that's a square root. Yeah, so the square root of some stuff. So we have some square root, some stuff. Let's write it down these three. So that will be, we need to take the derivative of this. So the derivative of outside function. That will be, so the square root will also know that's just an exponent, right? So that's some stuff, some inside stuff, to the power of 1/2, right? So we know that. So we just have to apply the power rule here. That will be 1/2 and subtract 1. So that will be minus 1/2. Right, so, and this stuff is actually, inside we have x squared plus 1 cubed. So, good. Now, we move further. We move inside, right? We move layer by layer. All right, next layer is going to be x squared plus 1 cubed. So, we see also, there's just some stuff to the power of 3. So, some stuff cubed. So, we need to apply the power rule again. That will be 3 x squared plus 1 squared, right? So we bring down the exponent and subtract 1. So that will be 2. And we continue. It didn't end yet. So, and now we also look at x squared plus 1, and that's the last layer, basically, hopefully. So this is the last inside function, and we take the derivative, that will be 2x. So this is end. This is the end. So this is the derivative of this function. It kind of looks hard, but that's why it's chain rule. Yeah, it can go really far. Wonderful. Next example, I think. Okay, also, of course, if it's hard, but I don't think so. I think it's better to learn to think about it this way, because just some stuff, yeah, just outside function inside some stuff. So you take the outside function, write it down, everything which is inside, then you multiply by the inside function, and so on, and you move further. We also, of course, we can use U notation, right? We all introduced earlier, but it takes more time. It takes more time. Imagine now I will say, okay, this is U. And then, so I have y is the square root of U. And I want to obtain dy dx, right? And that's dy du multiplied by du dx. I don't think that's easier. So we take the derivative with respect to U. That will be U 1/2 U to the power of minus negative 1/2. Right, so, and then we'll multiply by the derivative of du. So that will be, du is x squared plus 1 to the third. So that will be 3 x squared plus 1 squared. And what's funny, that's already, du dx, du is also, it also contains inside function. It's also a composition function, right? So that's the problem. I mean, now we just have to, if you try to follow this rule, then you have to now bring some new variable, say, okay, dy dx is equal to, dy dx is equal to dy dk multiplied by dk dx, where dk is x squared plus 1, because that's just some inside function, right? And so on. And you move and move further. Okay, that's not x squared plus 1, that's actually, oh yeah, it's x squared plus 1. So you move further this way. And that's kind of, it takes more time, I think. Just easier, but of course that's basically the same thing, of course. But it's better to learn to think about it this way, just, some outside function of some stuff, boom, 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 next. Now I move to the next layer, boom, boom, boom. Next layer, next layer, next layer, and till the end where you have some just simple function from the previous lesson, right? The simple function, you say, okay, this is the end, this is the end. The simple function from the table, no chain rule anymore. All right, let's try to solve next example. All right, let's solve a harder example. Let's say y equals x squared multiplied by cosine 5x minus x cubed plus 1 over sine of 2x. Or no, let's also change the function. Let's say natural log of 2x. So I guess you already see that that's going to be a huge x squared. That's going to be huge, really huge example. And first of all, ultimately, the chain rule is general rule. Believe me, all the other rules we discussed before, they're just special cases of the chain rule. Because imagine if even we take the derivative of x to the fifth, right? So according to the power rule, that will be 5 multiplied by x to the fourth. And if we think about it in terms of chain rule, right? So that this is some stuff, something to the power of 5. So we bring down 5, we apply the power rule, of course, we bring down 5 and multiply by x to a fourth. Some stuff to a fourth. And then we can apply the chain rule again, because now we take the derivative of the inside function, right? So the inside function is x. We take the derivative of inside function, and that will be x prime, right? So what's the derivative of x? That's 1. That's the main idea. That in fact chain rule works every time, always. But at some moment of time, you just, you take all the layers, right? And then you get to a point where you just, you get to a point where the inside function is just x, just the variable. And then if you take the derivative of the x, that will be 1. So it doesn't change a thing. Of course, we just do not write it. Therefore, the chain rule, the name chain, right? So you go through all the derivatives, outside, inside, outside, inside, outside, inside, till to a point where you get the variable. Just I know the chain. You get you have to take the derivative of the variable, and then it's going to be 1. And so you just don't write it down. That's the end. That's the end of your chain at last. So this is how it works. Good. And of course, we already saw that this chain can be really long, can be really outside, inside, outside, inside, outside, inside. It can be really long. But I hope, of course, you won't face such problems in this exam. Of course you won't. But 3-4 chains, it can be. All right. So let's take the derivative of this function. That will be the end for the chain rule. Of course, you'll have to practice yourself. So let's find the y prime. So we need to find the derivative of x squared cosine of 5x minus x cubed plus 1 over natural log of x squared. Good. Of course, let's start with first one, this. So we look at that and we recognize what? We recognize the product rule first. So we have to use the product rule first. And that will be f prime of x, right? So that will be 2x, right? Multiplied by g of x, cosine of 5x. Wonderful. Then f prime of x, g of x plus f of x, g prime of x, right? So now now x squared chills and we multiply by the derivative of cosine of 5x, So that will be, but here that's going to be the chain rule. So now we have to take the derivative of cosine of 5x. So first, what's the outside function? Cosine. So the cosine of some stuff, we don't care. So that will be negative sine of some stuff, 5x. So of some inside stuff. And now we also have to multiply by the derivative of the inside function. That's the derivative of 5x. So that will be just 5. Good. So we finished the product rule. Wonderful. We move further. Minus. And now we work with this one. Here we'll have to apply the quotient rule, right? So that will be f of x, f prime of x. First we take the f prime. And that will be, no chain rule, boring, 3x squared plus 0, right? So of course the derivative of a constant, that's 0. So just 3x squared. And we multiply it by, so that's f prime of x, we multiply by g of x, so that will be natural log of x squared. Then minus f of x, x cubed plus 1, multiplied by g prime of x. So this is going to be again the chain rule, right? So what's the outside function? That's natural log of something. So that will be, what's the natural log? So that will be 1 over x of, so that natural ln x, right? That's 1 over x. The derivative of ln x, that's 1 over x. So it's going to be 1 over x squared, 1 over some stuff, x squared. And we multiply it by the derivative of the inside function. So that will be 2x. So basically, yeah, you can also in the moment say, okay, inside function, that's going to be u, right, for a moment in your head. ln u, so what's the ln u? That's 1 over u, and then you also, you just do it in your head. Then you replace u with inside function back, so instead of u, that's going to be x squared, right? So you just do it in your head, and okay, so 1 over x squared, great. Then you multiply by the derivative of the inside function, that's just 2x. So we finished with that. And of course, we don't have to forget to divide by a natural log of x squared. Wonderful. So this is y prime. Let me introduce y prime. And no, I'm not going to simplify it, sorry. I'm not going to do that. That was just for practice. Yeah, the most important thing was just applying all the rules, products, quotients, chain rules. No, I'm not going to simplify that expression, sorry. All right, I hope that's clear. Of course, you have to continue practicing, and if you have any questions, ask them. All right. And actually, one more thing to note about the chain rule. And because of the chain rule, sometimes you will see the tables, these derivative rules written in this form. For example, instead of just x to the n, right, you will see u to the n. And they will write that it's going to be n multiplied by u to the n minus 1, right? And also du dx. So it's like general rules, because ultimately, of course, as you apply the power rule, you make it, you also don't have to forget to take the derivative of the inside function, because usually, of course, that's all about composite functions. And if u is x, then that's just going to be 1, right? So that will be 1. So nobody cares. Therefore, it's the general derivative rules. And sometimes, you might see them this way, written this way. And every rule may be written this way, right? So the derivative of sine u, it just means that that's going to be cosine u and multiply by the derivative of the inside function of du over dx. So that's, as I told you, that's just some general expressions for chain rules. Not chain rules, derivative rules, all the derivative rules. And I think, I'm going to attach the general table, right, where you will have these general rules. But basically, this is the same rules we discussed previously, plus the chain rule. So instead of x, you're going to have u, and everywhere you will also have to multiply by du dx, which is the derivative of the inside function. And that's it. But I have to make sure that's familiar. That's something familiar. All right, up to this point in the course, all the functions, most of our functions, have been expressed in explicit form, right? So explicitly. Usually, any equation, right, we were solving it for y. So it was y equals and some square root of 3x squared minus 1. It's just some example. But however, it's not always the case. Sometimes we cannot solve for y. Sometimes it's really hard. And we have to solve an equation implicitly, right? Let's say we have to write it down in implicit form. And imagine now, let me give you an example. Imagine the equation is y cubed minus y squared plus x minus 4, I don't know, so equals 0. Is that really easy to solve for y now? I can say that's really hard. Yes, so it's really hard. I just was wondering if the example hard enough. So it's really hard. And here we're going to work with an equation in an implicit form. And imagine now, I want you to find, so before, for example, we solved for y, and then I asked you to find dy dx, the derivative of y with respect to x. I was wanting to find y prime, and that was easy. We were applying all the rules, chain rules, our tables and all the stuff. So then the answer is here. So let's actually do it again. So what's the outside function? The square root, yeah, the exponent. So we apply the power rule. That will be just some stuff. So now we have some stuff to the power of 1/2. So 1/2 goes here, and here we subtract 1, so it will be minus 1/2. And inside we have 3x squared minus 1. And then we're multiplied by the inside function. That will be the derivative of 3x squared minus 1. So that's going to be 6. So we bring down 2 here, so it will be 6x. That's all. And if you take the derivative of inside function, which is x, you're going to get 1. So we stop here. We already discussed that. So 6x. Wonderful. So this is what we did before. But now imagine I want you to find here dy dx. Is that end? If we can't solve for y, is there any other way to obtain the first derivative of y with respect to x? And yes, and we call that implicit differentiation. And the idea is that we are going to now differentiate with respect to x every term of the equation. Every term. Every single one. And then try to solve for dy dx. That's it. So it will be a bit different. That's why it's implicit differentiation, right? We're not solving for y in the first place. We're just taking the derivative of each term, and then we're trying to somehow factor dy dx. We're trying to solve for dy dx. So this is the difference. And let's try it out here. Now, you just have to understand what's y. Y is some function of x, some composite function, right? So I can't now just say that the derivative of... So first of all, I want to now take the derivative. So I want to take the derivative. Let's write it down this way, with prime. Just prime. Okay, actually, let's use dy dx this time. Minus. So I have to take the derivative of each term. Minus the derivative of 4. So this is it. Now we look at that. Y cubed. So what's the derivative of y cubed? And you have to understand, that's not just x, right? That's not just x cubed. That's not just 3x squared. No. This is some composite function. You think of it, that's a function. Therefore, we'll have to apply the chain rule here. That will be, this is just something cubed. So that will be 3 something squared, right? And we also don't have to forget to multiply by the derivative of the inside function. That will be dy dx. So here's where we get dy dx. Yeah, it appears here. Dy dx. Then we move further. This one. Again, we have to apply the chain rule. This is something squared, so that will be 2 something multiplied by something, right? Now we have to take the derivative of the inside function. That will be y prime, dy dx. We just have we don't know the y, we don't know the function, so we can't really find the derivative, you understand? I mean, analytically, we can't just write it down now, derivative of the inside function. So we have to just write down that dy dx, y prime, y as you wish. But let's reuse dy dx. That just means that we don't forget that that's a chain rule. We don't forget that that's a function, composite function. That's just a function of x. So we don't finish here. Dy dx. Then we move to the next term. And this is simple. That's just x. Have to take the derivative of x with respect to x. What's that? That's 1. So no chain rule here. And the derivative of the constant, that's 0. Beautiful. So that equals 0. And so the final equation is, and now we can factor dy dx, right? And inside we get 3y squared minus 2y. And that equals minus 1. So what's the dy dx? dy dx is minus 1 over 3 y squared minus 2y. So this way we found the derivative of y with respect to x. So this is implicit differentiation. Let's actually practice more, of course. One more example. Alright, and I've found a beautiful example. So we want to find the slope of the tangent line at this point, right, implicitly. So this is our function. And usually, yes, some kind of circles and other stuff, they usually written in this form. That's just more convenient than, imagine if you solve for y, you will get some two roots, right? You'll have to write plus, minus, and the square root. So instead of that, we use usually implicit form. And now, instead of solving for y and all that stuff, we can use implicit differentiation if we want to find the slope. The same thing, right? So this is our equation, x squared plus 4y squared equals 4. Now, if you take the derivative with respect to x of every term, that will be the derivative of x squared plus the derivative of 4y squared and the derivative of 4. Good. So let's break this down. The first one, the derivative of x squared, very easy. No chain rule, right? That will be just 2x. Or in fact, there is a chain rule, but when you take the derivative of x, that's going to be 1, right? dx, 1. Good. Next one. We move here. Now, we keep the constant, pull the constant out to the front. Now, we just care about y squared. And of course, that's going to be the chain rule. So we just have something squared, right? So that will be, we bring down 2, multiply by the inside function y, and we don't forget to multiply by the derivative of the inside function. So this is dy dx. Exactly what I'm trying to find, the slope. So, and that equals to what? That equals 0, right? The derivative of constant, that's 0. So this is our equation. And let's also write it down. So that will be 4y dy dx equals 0. So we have to solve for dy dx because we want to find the slope. And that will be minus. So this will be negative 2x over 4y. So that will be negative x over 4y. So this is it. And now if we want to find the slope at some point, we just take and substitute the values. Nothing is hard. So dy dx, the derivative, the slope at this point will be what? That will be, instead of x, we put the square root of 2 and 4 multiplied by this thing. So we get, okay, let's just write down this way first. And we see that that just will be, 2 will go to the top. So that will be, and minus, multiplied by minus will be plus. So that will be just 2, right? Because the square root goes to the top. So that will be 2 over 4. So that's just 1/2. So the slope of the tangent line to this curve at this point will be 1/2. So beautiful, really. And in this case, if you would solve for y, then try to take the derivative, you would do much more steps. So implicit differentiation really is a useful tool sometimes. That's true. All right, 2 more examples. So this is our equation, y cubed plus y squared. But basically, of course, we solved similar, 5y minus x squared, and that's equal to minus 4. So again, the first thing we do, we take the derivative of each term now. So that's going to be, let's even not write it down. So that what will be the derivative of this term? That will be 3y squared, like apply the chain rule of course here, and multiply by the derivative of the inside function. That will be dy dx. Next, again the power rule, dy, and multiply by the derivative of the inside function, dy dx. Next one, again 5y, that's again a function, composite function, so that will be 5. However, so what's the derivative of the outside function? That's 1, but we also don't forget to multiply by the derivative of the inside function, that's dy dx 2. And minus x squared, so that will be 2x, and the derivative of the inside function, that will be dx dx, that's 1. So, and this is going to be the derivative of constant, that's 0. Wonderful. And now we just have to factor dy dx, and we get that dy dx multiplied by 3y squared plus 2y minus 5 and equals 2x. So dy dx is equal to 2x over 3y squared plus 2y minus 5. So this is the answer. Very easy. In fact, it doesn't take too much time, I guarantee you. So fast. And the last example with one more slope, because usually in fact we use it for slopes, for some graphs, some really strange graphs, complex graphs, and that's really useful when it comes to weird graphs. Alright, so last example for today. Imagine we want to find the slope of this strange curve. And again, of course, it's much easier and it's really hard to solve it for y, so it's given in an implicit form. And imagine we want to find the slope at some point 3, 1. So we want to find the slope at this point. And of course, it's better to not try to solve it for y, just use implicit differentiation. And let's do that here. And again, we will see that implicit differentiation is actually a beautiful thing. So this is our equation. And we want to do what? So we have to take the derivative of each term, right? We have here. So we take the derivative of 3. So here we'll have a bunch of chain rules, guaranteed. And so therefore, that's a beautiful example. The derivative of these. And also products. Oof, that's so beautiful for the, that's really good for the end of the lesson. So we finish everything we've covered today. Wonderful. So let's start with that. Of course, we keep the constant here, so 3 stays. Now we need to deal with that. And that's a chain rule first. So that's something squared. So that will be 2 and something to the power of 1. So that's just x squared plus y squared. Wonderful. Now then we move further. So we move further. Now we take the derivative of the inside function. That will be multiplied by the derivative of the inside function. That will be 2x, right? No chain rule here anymore. Plus the derivative of this. So that will be something squared. So that will be 2y multiplied by the derivative of the inside function. That will be dy dx. Good. So we finished with the left side, and that's equal. Actually, I hope we'll have enough place. Now we keep 100. That's a constant. We keep 100 here. Then we have x multiplied by y. So that's going to be the product rule. And we have to take the derivative f prime of x multiplied by g of x, right? So we have to take the derivative of x. That will be 1. So that will be 1 multiplied by y, g of x, plus f of x, so that's just x, multiplied by g of x. So that's y here. So we have to take the derivative of y, and that will be something to the power of 1. So that will be 1. But we also don't forget to multiply by dy dx, right? So the derivative of the inside function, so that will be dy dx. And that's it. Now let's write it down properly. So that's 6x squared plus y squared multiplied by 2x plus 2y dy dx. and it equals 100 y plus x dy dx. Great. And actually, I don't want to continue that. That will take a bunch of time. But truthfully, you can solve it. So, and it's not hard. Now we just have to, okay, it's kind of messy, of course. Now we will have to multiply. And so simplify all that, then factor dy dx and solve for dy dx, but it can be done. We already see that it can be done. No, I'm not going to do that, sorry. All right, that's all. Well, that was all for today. Yeah, next lesson we're going to talk about the higher order derivatives. That's also going to be cool. And plus we're going to talk about inverse differentiation. It's also super important. And overall, practice, practice, and practice. If you have any questions, ask them. And happy studying and smash AP, smash AP. See you soon.